Notes 6.1 are about the area between curves. We have a diagram here of a curve y equals f of x, and we have a region from x equals a to x equals b, and we've shaded that region here for you. The area of that shaded region is the integral from a to b of the function that is the upper boundary. So the lower boundary is the x-axis, and it's bound above by y equals f of x. So we'll handle this with an example. Determine the area of the region bounded above by this function and below by the x-axis, and then the lines x equals 1 and x equals 5. Picture of this would look similar to the one on the left. The curve 1/4 x squared plus 1 is going to be a parabola opening up, and the region we're interested in is this region right here. So set up an integral from 1 to 5. Your function 1/4 x squared plus 1 is the integrand, and your variable of integration is dx. Take the antiderivative, we get 1/12 x to the third plus x, and we're going to evaluate from 1 to 5. This is 1/12. 5 to the third is 125 plus 5, and then subtract. Now substitute in the 1, so we get 1/12 plus 1. The first parentheses is 125 twelfths plus 5, and then for the second parentheses I'm going to distribute the minus, so I'll get minus 1/12 minus 1. So I could do 125 twelfths minus 1/12 is 124 twelfths. 5 minus 1 is 4, so that's 124 twelfths plus 4. The first fraction reduces to 31 thirds, and if I change 4 to a fraction with a denominator of 3, I get 12 thirds for a total of 43 thirds. This is a basic area formula for a curve, a region between that curve and the x-axis. But what we want to focus on in this section is area between two curves. So something more like this diagram, where we have y equals f of x bounded above, y equals g of x, which is a lower boundary below. Notice how f is completely above g. So f is greater than g in this situation. F is greater than or equal to g. And again, we're going from x equals a to x equals b. To find the area of this shaded region, I'm going to subtract. Take f of x minus g of x as your integrand. Our next example is f is x squared minus 2, g is 1/2 x plus 1, and a quick sketch of those. F is a parabola opening up, and it has a vertex at 0, -2. If I make a substitution such as x equals 2, I'll get 2 squared minus 2 is 2, and if I try -2 squared minus 2 is 2. Therefore, I could see the symmetry for that parabola. And then g is a line going through 0, 1. That's the y-intercept. Slope of 1/2. It's also going to go through the point 2, 2, and it's going to go through the point -2, 0. So the region created by these two graphs is this region here that I'm shading. So we are noticing for that shaded region, g is greater than f. So g is above f in this situation. So when I set up my integral, I'm going to have g minus f. I'll write it first that way. And then I have to figure out where these curves intersect. It's easy to tell on the right side. When x equals 2, the f of 2 value is 2, and when g of 2 is evaluated, we also get 2. So we know that the interval ends at 2. But over here on the left, where do they intersect? So you're going to have to let f equal g in this case. X squared minus 2 equals 1/2 x plus 1. So let f equal g and solve. So I'll get x squared minus 1/2 x minus 3 equals 0. I'll multiply through by 2, and then I'll factor. So x equals -3/2 and +2. We already knew that the upper bound on our integral was 2, so that all we have then is the lower bound, which is -3/2. So go ahead and put the actual functions into the integrand. First is g, 1/2 x plus 1, and then subtract f, which is x squared minus 2. You'll have to put parentheses around f, because when we subtract, we need to distribute that minus. -3/2 to 2. Our integrand becomes 1/2 x plus 1 minus x squared plus 2. If you want to, you can put the 1 and the 2 together. So the integral from -3/2 to 2 of 1/2 x minus x squared, and 1 plus 2 is 3. And now an antiderivative. 1/4 x squared minus 1/3 x cubed plus 3x. So the first parentheses, I'm going to substitute in 2. And the second parentheses, I will get, and I end up with 343 over 48. Now we are going to do an example that involves trig functions. Let's graph secant squared on the interval from 0 to pi over 4. The secant of 0 is 1, and 1 squared is 1. Now I'm going to try pi over 4. The secant of pi over 4 is the square root of 2, and the square root of 2 squared is 2. So I have 0, 1, and pi over 4, 2. Secant is increasing on that interval. Now for sine. At 0, sine is 0. At pi over 4, sine is root 2 over 2, which is about 0.7. So we have a point at 0, 0, and pi over 4 is about 0.7. And we know it's concave down from 0 to pi over 4, so it's going to look something like that. The area between those curves from 0 to pi over 4 is this region in here. That's the region we're finding. The upper bound of that region is secant squared, and the lower bound of that region is sine. So set up the integral from 0 to pi over 4. The upper bound to the region is secant squared, minus the lower is sine, and write the variable of integration dx. Antiderivative of secant squared is tangent. The antiderivative of sine is negative cosine. So we will have tangent plus cosine. Evaluate from 0 to pi over 4. The first parentheses, the tangent of pi over 4 is 1. The cosine of pi over 4 is root 2 over 2. The tangent of 0 is 0, and the cosine of 0 is 1. So do you see we have a 1 minus 1 here, 0. So the answer is simply square root of 2 over 2. The next example is for our graphing calculator. We're going to enter in f equals cosine into y1, and we'll enter g of x is x over 3 plus 1/3 into y sub 2, and we'll get a sketch of that. You can sketch it on this graph I've given you, or you can just look at it on your calculator. So let's move over to the calculator and solve the problem from there. Go to y equals, enter in cosine x, hit enter. For y sub 2, let's enter x divided by 3 plus 1/3. And we are graphing a trig function, so we'll make sure our mode is radian mode. And we can use the zoom feature. Choice 7 will give us a trig graph, which means our x-axis is set up pi and 2 pi, and we are interested in this area of the graph where they intersect and create regions. If we wanted to, we can just box this and look at this. That's another feature under zoom. Zoom box is choice 1, and you can move your cursor to the upper left corner of your virtual box and then move it to the bottom right corner. So we're going to start by moving the cursor up, and then we're going to move the cursor to the left. When you get to a good place, that would be the upper left corner of the box, hit enter, and then when you hit your right arrow or your down arrow, the box will start to take shape. When you've enclosed the region that you want to emphasize, you hit the enter button. We care about this region being enclosed on the top by the linear function, so that's in y sub 2, and on the bottom by the cosine function. So this part of our work is going to be the y sub 2 minus y sub 1 in the integrand. Then when you talk about this region here, it's being bounded above by cosine and below by the linear. So we're going to do cosine minus the linear in the integrand for that part. What we really need are these intersection points. So we're going to get these intersection points, and we need their x-coordinates. So when we find the x-coordinate at each intersection, we're going to store them. We'll store this one in A, we'll store this one in B, and we will store this one in C. So let's find this intersection point first. Go to Second, Calc. Intersect is choice 5. They want to know a first curve, second curve, and a guess. So we can hit enter on the cosine curve, enter on the linear curve, and then our guess is going to be over here. This is negative pi at this location. Each of these tick marks is a pi over 2 apart. So I'm going to put in a negative 3.2, and that'll get our cursor over here. So I'm going to type in negative 3.2 to get the cursor closer. And there we have it. So there's the x-coordinate of that intersection. So go to the home screen, hit second, quit, and when you hit X, enter, you'll see that negative 3.638. And let's store it in alpha A. Hit enter. We have that first intersection point found out. Hit the graph button. So we know what this spot is right here, and we stored it in A. So that'll be the lower bound on the integral when we find the area of this region. Now we need the upper bound. We need this intersection point. So we'll do this again. Second, Calc, 5, and I'll arrow to the right a few steps. You can see it sitting on the cosine curve. You can see that up here because it's typed up here as well. Hit enter, enter, and then we want to scooch over here. That's about negative pi over 2. You could type in like a negative 1.5 perhaps, and when you hit enter, it should pop to that location. If that didn't happen, I would enter a different number, or I would scooch the cursor closer and hit enter. Okay, we have the X location of that intersection, so we're going to go to the home screen, second, quit, hit X, hit enter, and you could see that value. You can go store alpha B, and it's stored in B for us. Go back to the graph. We want this last intersection point here. This is closer to pi over 2. We're going to hit second, Calc 5, and enter, enter, and then we need to scooch over to there. So it's about pi over 2. So I'm going to type in 1.5, and it'll pop over to that location. There's our intersection location, so 0.889 will be our C value. You can hit second, quit to go to the home screen. You can hit X, and you could just go store alpha C right away, and you could see the 0.889 right there. We're now ready to calculate the area of these regions. We just need to remember what order to do it in. The first region has the linear on top, and we stored that in y sub 2. So when we set up the first integral, we're going to go y sub 2 minus y sub 1. Then when we set up the second integral, we're going to do y sub 1 minus y sub 2. Remember, it's the curve that's bounding on top minus the curve that bounds the region on the bottom. Let's go to the home screen and set that up. I'm going to clear this away. And we want the integral, so that's math 9, and we're going from alpha A, so hit alpha A, and you can arrow to the right and it'll jump to the upper limit, so you could type in alpha B. And then for your integrand, remember this is y sub 2 minus y sub 1, the linear minus the cosine. So I'm going to go to vars, y vars, function, and grab y sub 2, so arrow down, and we have y sub 2 entered in. Now hit minus, and vars, y vars, function y1, arrow to the right, and that will be a integral with respect to x. Add that to the region bounded from our b to c, and it's going to be y sub 1 minus y sub 2 this time. Let's pull the integral out of the math menu, choice 9, and now we're going to go from b to c. So hit alpha b and then arrow to the right, alpha c, arrow to the right, and now we're going to do y1 minus y2. Don't forget to put in x for the dx for variable of integration and hit enter. The answer is 1.662. This last example presents an interesting situation. We'll start by getting the graph set up. The graph of y equals the square root of x starts at 0, 0, and the square root of 1 is 1, the square root of 4 is 2. So I can see the curve, the square root of x here. And x equals 3, y equals 1. When x equals 4, y equals 2. So the other line is graphed like this, and we're staying in the first quadrant. So the x-axis serves as the lower bound from 0 to 2. So we have this region, and then we have a new lower bound from x equals 2 to x equals 4. So that's this region. We actually have two separate integrals to set up. The first one from 0 to 2 is just the upper bound is the square root of x and the lower bound is 0 for y equals 0. And then the second integral is going to go from 2 to 4 with the subtraction. Square root of x is the upper bound and x minus 2 is the lower bound. So the setup looks like this. From 0 to 2, we just need the square root of x dx and add the integral from 2 to 4 where we do subtracting. So the square root of x minus 2 will be our integrand. If we handle these separately, we'll get antiderivatives of 2/3 x to the 3/2, evaluate from 0 to 2, and then we'll get 2/3 x to the 3/2 minus 1/2 x squared plus 2x, evaluate from 2 to 4. You could see I distributed the negative at the same time as finding the antiderivative. When you work this out, the answer becomes 10/3. There's a couple of things that you should notice about what we've done here today. We have been looking at graphs where we have an upper bound to the area, and it's usually in y equals form. So we've been saying y equals f of x, and then we have a lower bound to the area of the region, and we've been calling that y equals g of x. In some respects, the f of x being the upper bound is like the high boundary, and g of x being the lower bound is like the low bound. So some teachers might refer to this as y high and refer to this as y low, which means we have a function written in y equals form, and the high one represents the upper bound and the low one represents the lower bound, and we're going on an interval from a to b. So your basic setup is the integral from a to b of y high minus y low, and you have a dx there. It's in y equals form, and we have the variable of integration as dx. Well, you should know that there are going to be some regions where it's easier if you do not use y high and y low. Just imagine a region like this and like this, and these curves are not going to be written in y equals form, they're going to be written in x equals form. So this is going to be x low because it's on the left side, and this is going to be in x equals form, and it's considered x high. And you're going to find the area of this region, let's say it's right here, and we don't say from A to B, let's say the region starts here. So this shaded region is what you need the area for. We say C to D, so it's with respect to the y-axis now, not with respect to the x-axis. So such a region, which is better defined by x low and x high, would look like this. You would go from C to D, that part's probably easy, but you have to remember to go from x high to go x high minus x low for the integrand. And this time you're integrating with respect to y. So since the interval for your integral is described with respect to the y-axis, you're going to have a variable of integration as dy. And the best thing to do is just give you an example right away where this can happen. So if we had y squared equals 3x minus 6, and we had y equals 2x minus 8, switch this first equation into x equals form. So I'm going to add 6 to both sides and divide by 3. So I'll get x equals y squared plus 6 divided by 3. This one is easy to switch into x equals form. I'm just going to add 8 and divide by 2. This first one's a parabola, and a y squared parabola opens to the right or left. So it's going to look like this because the y squared is a positive coefficient, so we are going to open to the right. And then you know what a line looks like. That's a line going through -8 as a y-intercept and as a slope of 2, so it's going to slant to the right. The region we're trying to find is this region here. And it's best described by using an x high equation and an x low equation. So high is always on the right and low is always on the left. When you set up the integral for this, you're going to go from c to d, and I'll tell you what those are. They're not nice numbers. C is about -1.812 and d is about 3.312. So your integral is going to go from -1.812 up to 3.312, and we have to do x high minus x low. Well, the high one is the line, so that's y plus 8 over 2, and then subtract the low one, which is the quadratic one, so that's y squared plus 6 over 3, and you're going to integrate with respect to y. We can use our graphing calculator for this one, and then the result is about 7.472.